Hello everybody. In this video, we're going to be talking about how we navigate the night sky. How do we actually locate things in the sky, and how do we communicate both for our local skies and in a grand sense so we can put everything that have a fixed address in the sky. This is some of the more subtle, more difficult to grasp material that we're going to go over in Unit 1, Part 2. And what I'm going to do is I'm going to introduce this material, and then we are going to go through a series of demonstrations using a program called Stellarium. Those are going to be in a different video. This video is going to be a little bit long, so go ahead and buckle up. Feel free to pause and digest as much as you want to. I'm going to introduce you to the night sky. So how do we go about navigating the stars? Here we have this wonderful person that's doing this beautiful observations out in very, very, very dark skies. And let's say that this person right here wanted to communicate with us where we can look to see the Lagoon Nebula, which is right here within the Milky Way, this red part, this red sort of blob right here. So how could we communicate how to find the Lagoon Nebula? That is going to be our task. We basically have two different ways that we can approach describing where is the Lagoon Nebula. If we were up on this staircase with the person, we could just go ahead and go with a look over there sort of method. Basically, they could point, and what they'd be doing is they'd be pointing in a certain direction, that way, and up so high. So we can have a look over there sort of coordinate system, which is going to be one of the two that we explore. So they could say, hey, look due south and up 30 degrees from the horizon. That's where you'll find the Lagoon Nebula. Okay, that's pretty easy to get. But what if we wanted to communicate with somebody else that lived in a different part of the world, where their local sky is going to look different? Saying to look south right now and up 30 degrees is not going to work. What we need is a map of the sky, a coordinate system on the sky that is fixed for everybody, no matter where you are, when you are. This one is the hard one to get and to understand. But if you're familiar with how you do graphs and XY coordinates, that's going to help you with this one. To help you along with that, I have created an XY grid right here on our picture. And this person might communicate to me that the Lagoon Nebula lives in the sky at coordinate X, at coordinate X, comma Y. So you have to go to this part of the sky and then up to this part of the sky. Of course, we're going to imagine everything on a sphere, so it'll be a little bit different than this sort of flat grid that we have right here. But this would be another way to do it. So this person could say that this is that coordinate. Let's call this 0 down here. So we'd have 1, 2, 3, 4.25. And that would be the y coordinate. And the x coordinate would be 1, 2, and call it 2.25. So 2.25 over 4.25 up. I know, that one's going to be where we spend most of the time, and trust me, the videos whenever we go over the Equatorial Coordinate System, our coordinate system for the sky, our grid for the sky, will be one that you want to review. All right, so if we're going to talk about how we look in the sky, let's start local, the easier one to deal with, the sky that we live with day in and day out. What I'm going to do is I'm going to put a little bit of legs on how we can communicate about the sky. I'm going to introduce some terminology that'll probably be new to you. The one that's not so new, and I'm going to say this exactly as I mean it, your horizon. So imagine that you're at the beach, or go outside and look towards, just look out. What if you're at the beach and you look out? The horizon would be the point that would separate the ocean from the sky. If you're out in the Midwest, where you have nice flat landscape, it would be where the ground divides the sky. So it is the line that separates the sky from the earth. It's whenever you look out, it's what's straight ahead. So if I look out, I can define my local horizon by what is straight ahead of me and what divides the sky from the earth. A new point that you maybe have never heard of, it's a fancy term for a relatively simple concept, zenith. So if you point straight up and look straight up, so what is directly above your head, that point on the sky is defined as your zenith. So zenith is the point directly overhead. And now we are equipped with to define a line that will cleave the sky into an eastern half and a western half, allowing us to talk about the eastern half of the sky and the western half of the sky. So this thing that splits the sky is what we call the celestial meridian. Usually we just say the term meridian, And what you want to do to define your meridian is you would look due north, so you'd point due north, and then you would carve a line through the sky that goes up to directly overhead through your zenith, and then comes down and points at due south. So a line that goes directly overhead and connects north to south. That's represented here by this pink line. So it's going directly from north through the zenith down to south. And now we'd have the eastern part of the sky over here and the western part of the sky over there. All right, so far, not that bad. Just some terminology that will become a little bit easier to use with. But now let's actually talk about how we can point to specific locations in the sky. Now, this is going to be the first of our two coordinate systems that we talk about. This is what's called the horizontal coordinate system. It is the coordinate system we use for our local skies, the ones that work for where you are right now. And unfortunately, if you're somewhere else at a different point, this system is not very good for communicating with your friends. So you can't call up your buddies in California and give them the location of something in the sky in horizontal coordinates. All right, so what are our horizontal coordinates? And let's look at the word first, horizontal coordinates. So we have horizon right in there. So these are the coordinate systems that are associated with the local sky, which we can find by your horizon. So you have your horizontal coordinates. And the two coordinates we're going to use are basically what direction and how far up. Let's start with the what direction. We call the what direction the azimuth, or azimuth, as people usually say it. So what is our azimuth? So if you point due north, and I'll pretend like you all in the screen are, that's due north, we would define that as 0 degrees of azimuth. So north is 0 degrees, and then I'll rotate clockwise. So I'm rotating to the east, and I'd be just ticking up the number of degrees I'm rotating. So if I point due east, I'm now at 90 degrees azimuth. As I rotate to due south, I'm at 100 degrees of azimuth. As I point to due west, I'm at 270 degrees of azimuth, and then back to 0 at north. So it's just the number of degrees you are away from due north, moving around from north to east to south to west, and just counting up the degrees. So it just tells me how far do I spin around. And then we have the how far or how high do you point up. So notice that these are measured in degrees. So azimuth is in degrees, and altitude is also going to be in degrees. It's going to tell me how many degrees I look up. Let's define a couple of waypoints. So 0 altitude would be straight ahead. I'm looking out to my horizon. So my entire horizon has an altitude of 0 degrees. How far can I look up? Well, I can go until my neck hurts, pointing straight up at 90 degrees. So altitude is limited from 0 to 90 degrees, from straight ahead to straight up, while azimuth was 360 degrees around. Okay, so it's just how many degrees am I pointing up from 0 to 90? Now let's take an example that's here sitting in my background. I have this picture of Jupiter in the background. So what would its horizontal coordinates be? What would be its altitude and azimuth? What we typically just say, it's alt as coordinates. Alt for altitude, as for azimuth. All right, let's take care of the azimuth first. So here, north is 0 degrees. I'm spinning around to about 180 degrees, maybe add another 5 degrees, 185 degrees of azimuth. So I now have one of the two coordinates. Now how high do I have to point up? Pointing up, not quite 45 degrees, maybe call it 35 degrees. So that picture in my local sky of my room would have an azimuth of 185 degrees and an altitude of 35 degrees. So you can start picking up things, go outside is probably the easiest. And you can see that if you wanted to tell somebody where, hey, where's the sun at right now? You might want to tell them an altitude and azimuth. It's always moving, so those coordinates are always changing for the sun. But it tells exactly where to look in the sky. This is the coordinate system that I was using quite frequently, and the one that I use most often as an astrophotographer. So whenever Comet Neowise was up in our skies, whenever people are asking me how to find Comet Neowise, I would tell them what day to look. So let's say this Saturday, and then I'd tell them what direction to look. So it might be, okay, look due north and then up 30 degrees. And then whenever it switched to the other side of the sky, look to the northwest and up 15 degrees, something like that. So you, again, azimuth would be how far around, and you can give it in degrees, or if you just want to do rough things, you could say north, northeast, east, southeast, south, southwest, west, northwest, north. Okay, that one is fairly easy, but it's only good for right here, right now, which will be demonstrated on the video. Now I want to go ahead and give you a little bit of a sense of why all of these coordinate systems are going to be a little bit difficult to get here. Because let's take a space-based view. We live here on Earth, so it's very easy for us to think about things in the local sky. It's hard for us to think about the Earth rotating around on its axis and orbiting the sun all simultaneously. It's kind of a dizzying view. So what I'm going to do, and since we're going to see images like this, and you're seeing images like this in my textbook, I want to go ahead and show you and describe what these are. So here's the Earth. We're looking down on the north pole of the Earth, and when we do that, that means that the Earth would be rotating counterclockwise. So this is the direction of rotation. So that way would be east, that way would be west, direction of rotation. And it's rotating counterclockwise, and it would be orbiting the sun counterclockwise. Now let's draw some points. If we're standing right here on the Earth, we could go ahead and draw our horizon. Remember, we're really tiny standing here on the surface of the Earth, so we can't see around the Earth. So this direction would be towards our eastern horizon. This would be towards our western horizon. Out towards me would be the northern horizon. Into the screen would be the southern horizon. We could draw a point that would be directly overhead. That would go to our zenith. And since it's going from the northern part to the zenith down to the southern part, that's also our celestial meridian. Kind of confusing to look at it like that. Maybe it helps if I put our sort of local view superimposed on there. So here we have our celestial meridian, and now you can see the dome in the sky, and you can imagine spinning around an azimuth and up an altitude. But this is a little bit problematic because what's happening all the time, the Earth is rotating. So this entire local sky, what stars would be pointing at, what stars are up, and whether the sun is up is constantly changing. So it's kind of dizzying to think about this. The Earth is doing this once every 24 hours. All right, so now that we have a sense, and you can see one of the problems with the horizontal coordinate system is since the Earth is rotating, so this would be pointing towards our zenith. Oh, sorry about that. Pointing towards our zenith. And you can see what our zenith is pointing at is constantly changing. Everything is changing in its horizontal coordinates. From our perspective, however, this is what it looks like. It looks like the stars are rotating around. Now the sun would be rising, moving, crossing the meridian, and setting. And the same thing with the stars. They rise and they set. So from our earthly perspective, we don't notice us orbiting around the sun. We don't notice us really rotating. What we do notice, it looks like everything else is moving around us. Which, if everything is moving like that, so notice that everything is moving, everything is changing its altitude and its azimuth all the time. Wouldn't it be great if we had a coordinate system, a way to just say, hey, this star lives here. It is always at this coordinate, and then all you have to do is know how to find those coordinates in the sky, be able to determine whether they're up or not. And that's why this slightly more complicated coordinate system, the coordinate system that basically the Lagoon Nebula lives at this address, this XY coordinate, it has this place in the sky, and that will fix everything in the sky, like the constellations, the background stars appear fixed. So we can navigate that way, and we can give everything its local address, a local coordinate that says, hey, all the stars live here. That would be a very, very useful thing, because then we don't have to worry about the fact that as the Earth rotates around, is changing the altitude and azimuth of everything in the sky constantly. And it wouldn't matter where you are on Earth either, because these are external to the Earth. These coordinates are the ones that define the sky. This one requires a good bit more work. So let's go ahead and take a look. And let's go ahead and imagine we went outside. We're looking up at the heavens. We're looking at the sky. And it feels like you're sitting inside the sky as this giant dome over your head. Looking straight out is your horizon. If you're looking straight up, you're looking towards your zenith. You have this huge dome over your head. If you're on the North Pole, it would be this dome right here. If you're on the South Pole, it'd be this dome right here. So what you can see in the sky is clearly going to depend on where you are on Earth. The North Pole observer can see this northern part of the sky. The Southern Pole observer can see the southern part of the sky. And if we take those two hemispheres and put them together, you can imagine this giant sphere that encircles the Earth, and we could put all the stars on that sphere. The Earth sits inside of this sort of hollow sphere that we can imagine, the sphere of the stars, this celestial sphere. And then the stars are hung on the inside of that sphere, and the Earth is just sort of rotating around inside of it. If you really want to think about it, you could imagine, like the Greeks did, that the celestial sphere rotates around the Earth, but we know that the Earth is the one that's doing the rotating now. And in fact, the Greeks actually thought, they took this idea of this celestial sphere, of let's imagine this sphere all the way around that encircles the Earth, and we can hang all the stars on the inside of the sphere. They weren't hanging the stars on the inside of the sphere. They thought there was a real sphere that had these little tiny holes in it, and it was the light of the heavens streaming down through the holes, and that's what the stars were. Okay, a little bit of extra information there, but here we have the Earth, and then we have this imaginary sphere where all the stars, we can put them on their point, the sphere, and we can define what's called the celestial sphere. This is going to be our concept. So now we have this globe of the stars that we can put a coordinate system on. Let's talk about some waypoints. How do we actually refer to things on the celestial sphere? We are not very creative folk, we astronomers, so we have our equator here on Earth. Let's just imagine extending our equator out on Earth until we can define a same thing on the celestial sphere. So just project this out, move this out until it hits the celestial sphere. You define this line that wraps all the way around, defining a northern part of the celestial sphere and a southern part of the celestial sphere. Let's call that dividing line the celestial equator. Just like on Earth, we define this as the equator. Told you that we're not very creative. Okay, let's also build some northern and southern waypoints. We have the North Pole on Earth, a clear geographic waypoint. Let's take the North Pole of the Earth and just follow it out until it hits its point on the celestial sphere. Same with the South Pole. Project that out until it hits its place on the celestial sphere. And we'll define what we call the North Celestial Pole and the South Celestial Pole. So now we have the northern part of the sky and the southern part of the sky, dividing them as a celestial equator, and we know that we have our North Celestial Pole and our South Celestial Pole. These will be our waypoints that we will use to build our grid on the sky, our coordinate system on the sky, our map of the sky, so we can chart and navigate and know where everything is out on the sky. Now we got to do the hard work of building that. So I've moved to just my own drawings. So let me explain what you see here. The sphere that you're seeing, here we have our celestial equator. So it's just a projection of Earth's equator out onto our celestial sphere. So this bigger circle is a representation of our celestial sphere, or the North Pole and the South Pole of the Earth. Project those out to the North Celestial Pole and the South Celestial Pole. And what we'll do, how do we actually navigate how far north or south you are on the Earth? Well, we use the coordinate on Earth, latitude. Knoxville's at about latitude 36 degrees north. So we know that it's about 36 degrees up this direction, north of the equator. We know that the North Pole is 90 degrees north of the equator, and we know the South Pole is minus 90 degrees from the celestial equator, 90 degrees south. So let's go ahead and adopt that moving north is plus, moving south is minus. And now let's take this idea of latitude, where how many degrees are you north? And let's take that same idea and project it out onto our celestial sphere. So we will literally take Earth's latitude system and move it and imagine it, the same idea on the celestial sphere. We can do that. So what is the latitude of Earth's equator? Well, that's 0 degrees. So the declination of our celestial equator we'll define as 0 degrees. But we're not talking about 0 degrees celestial latitude. That would be an intuitive name. It got called 0 degrees declination. So now we have the celestial equator is 0 degrees declination. The North Pole is 90 degrees north, and we said north is plus, so we'll call that plus 90 degrees declination. So plus 90 degrees declination. The South Pole is 90 degrees below the equator, moving down this way, so it would be minus 90 degrees declination. So now we can see that we can define declinations just like we define latitude on Earth, and they'll run from minus 90 at the South Celestial Pole to the equator at 0 to plus 90 at the North Celestial Pole. And notice if we keep going past north, we start just moving down towards the southern part, we're moving south. So we have between only minus 90 and plus 90. So we go from plus 90 to 89, 88, 87, 86, 85, blah, 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 back down to 0, and then all the way up to minus 90. Okay. Now I'm going to start adding more lines. And you could do this for every individual degree, but I want you to see just a couple of these so you can understand what's going on with declination. So if we were to go to 30 degrees north on Earth, take that line and project it out to the celestial sphere, we could define a ring of declination, just like we can define a ring of latitude on Earth. That would be 30 degrees north of the equator, and that would be our 30 degrees plus 30 degrees of declination. We can move up 60 degrees and have plus 60 degrees declination. And we could do the same thing, move minus 30 degrees for minus 30 degrees of declination, this ring right here, and minus 60 degrees for minus 60 degrees right here. Now I could do something like 45 degrees and I could draw another ring, and I could draw another ring for 46 and every little point in between, but this would become very, very crowded. So this is the same idea as latitude on Earth, and remember that you climb up the ladder on Earth, you climb the rings on declination. Okay, hopefully everybody's getting this, and it'll make more sense when we go through the videos as well, so I highly encourage you to watch the videos where I show these coordinates on the sky, because we've only done declination, which is analogous to Earth's latitude. What about longitude? How far east or west are you moving around the Earth? So for longitude on Earth, we define a 0 longitude. So how many degrees east or west? 0 degrees east or 0 degrees west as the prime meridian, which is just a location in England that people decide that this is our 0 point. So what can we do for the same idea except for the celestial sphere? Well, we won't just project the prime meridian. It's always rotating around here underneath the celestial sphere, right? What we need to do is define a 0 point that we can use then to describe how far east we are moving away from the 0 point. So how far are we wrapping around the celestial sphere? I do not expect you to remember the 0 point for the right ascension system, which is going to be the analogous coordinate to longitude, the one on the celestial sphere that tells us how far we're wrapping around the celestial sphere. But it does have a very precise definition of where the sun is located on the celestial sphere at the very moment of the spring equinox. So we define pretty much everything by the spring equinox when we're talking about charting the heavens. So the way I've drawn it, that would be right here, and then we can wrap around where we would just keep wrapping around. We'd be 0 to 90 degrees to 180 to 270, and that'll just define how far around the celestial sphere we're wrapping. So you can see these green lines are wrapping around it. However, the right ascension system, usually just called RA, is a little bit tricky because they do not define it by number of degrees that you're wrapping around the celestial sphere. That would make sense. What they do is they define it by number of hours you're wrapping around the celestial sphere, moving away from our 0 point. So our 0 degrees is really 0 hours. Why did they choose this, and why did they make it go from 0 to 24 hours? Well, there are 24 hours in the day, so the Earth is rotating through all 24. That your point overhead is going to be rotating through all 24 right ascensions, 24 hours of right ascension every day. The trick is what ones are up, what ones are the daytime, and what ones are the nighttime. That is not something I expect you to learn for this course, because the right ascension one is already, you're probably appreciating this, a little bit difficult to get. So the key point here is that we can wrap around just like we do with longitude on Earth. How far do we wrap around east and west? We can do the same thing on the celestial sphere, but instead of using celestial longitude, we call that the coordinate right ascension. Now, I bet most people's heads are spinning because this is pretty complicated, but I just encourage you to rewatch this video a lot. I'm going to show you some more examples of how we actually use this here in a second. So I encourage you to rewatch that. I encourage you to pause this and review some of the notes. And I encourage you to always anchor this back to, we can navigate and find unique places on Earth using the latitude and longitude system, which means we have this sphere that envelops the Earth, this imaginary sphere that we can put all the stars on. You can imagine it as a globe of the stars, and you can navigate it using celestial coordinates, what we call our equatorial coordinates. You can do that instead of using latitude and longitude, you can use declination, how far up and down, and right ascension. Okay. One thing I forgot to mention, that these are called equatorial coordinates. I apologize for that. So right ascension and declination, or RA and dec as we usually call them, are what we call the equatorial coordinates. And why do we call them equatorial coordinates? Because they're defined by the celestial equator. So here we have the part. So our equatorial coordinates for the celestial sphere, right ascension and declination, are defined by the celestial equator. Let's put all this together so you can see a practical example. So now I've put my lines of declination, my equatorial coordinates declination from -90 all the way to +90 in increments of 30 degrees. So you can see those in blue. And then in the green, I have my lines of right ascension from 0 hours all the way around to 24 hours, where each ring is, this would be 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6, so on and so forth, all the way around. So we have up, how far north and south, and how far around and around. Up and down and around and around. Sounds kind of familiar. Put them all together and you can see I've made this grid system for our celestial sphere. Let me show you how we can actually use this to put things, stars, and give them their unique addresses. Because remember, the stars are very far away, so they remain fixed in the sky on human timescales. Let's start with the star Polaris. Polaris, where does that live? Well, it's right at the North Celestial Pole, or very close to it. It doesn't follow exactly on it. So already I can tell, oh, well, Polaris is at the North Celestial Pole. It's our North Star. It should have a declination of +90. And pretty much is +89 1/4. So there is Polaris. And right ascension is how far you'd spin around this tight little circle up at the top. It would be 2 hours, so it would be 1, 2, and precisely right about there. So Polaris sits at the North Celestial Pole. Probably not surprised by this. What about the star Sirius, though? So Sirius is at right ascension, 6 hours, 45 minutes. So that'd be 6.75. 45 minutes is 3/4 of an hour. So I'd have to go to hour 6, one wrap around, 1, 2, 3, 4, 5, 6. Okay, so there's my hour 6 right on the very boundary here. It's at declination minus 16, closer to minus 17. So I'd have to go 17 degrees below the celestial equator, and I can pop Sirius. That's where Sirius lives on the celestial sphere. Hopefully you're starting to see why this is useful, because now we have a fixed place on the celestial sphere for the stars. Let's look at another star though. Let's go to Arcturus. And Arcturus has a right ascension of 14 hours. Let's not worry about the other part. So I'd have to go around all the way to 14. There's 6, 12, 13, 14. And it has a declination. So here I am at hour 14. It has a declination of about plus 20 degrees. So not quite all the way up to the 30. So it'd be at about right here in the sky. And then finally, it's not just for stars. We could use this for galaxies as well. So everything in the night sky gets its own location. So let's look at the Andromeda Galaxy, and where does it live on the celestial sphere? Where can I communicate to anybody its right ascension and declination coordinates, its equatorial coordinates? Where does it live on the sky? What's its address? So it has a right ascension of about 1 hour, just a little bit shy, and it has a declination of about 41 degrees. So 1 hour, move over 1 hour, and it goes up 42 degrees. So a little bit past 30, and right about here, and that's where Andromeda would live on the celestial sphere. Okay, those are the slides I wanted to give you to introduce these. We are going to actually spend some time projecting these coordinate systems on the night sky, which will hopefully hammer in all of these points and give you something where you can actually imagine it here on Earth. So whenever you go out and look at some beautiful night skies this semester, you can picture the coordinate systems on the skies. Thank you for tuning in. I hope you revisit this video often.